Welcome back, AP Chemistry students, to Unit 7, Equilibrium. Today we will be talking about Unit 7.2, Reaching Equilibrium and doing calculations at equilibrium. So if a system is not at equilibrium and you're given its concentrations, you can determine if the reaction has reached equilibrium or not by setting up what's known as a reaction quotient. You're going to question if you're at equilibrium. Get it? That's why it's given the variable Q. Now, calculating your reaction quotient is exactly the same way you calculate equilibrium position. It's the ratio of products to reactants. And once you calculate a value for Q, you need to compare it to the given equilibrium constant, or your predetermined equilibrium constant. If they're the same, congratulations, you are at equilibrium. But if they are not the same, you turn your inequality into an arrow, and that shows you which direction the reaction is going to favor. So if K is less than Q, that means that you have more products than reactants than your equilibrium is supposed to have. So you'll favor the formation of more reactants. If K is greater than Q, that means that you have more reactants. That means that your ratio of reactants to products is too small, so you have too many reactants. So the reaction will favor the production of products. And again, if K and Q are equal, then you're at equilibrium and everything is all good. So exercise 6 gives us 3 different reactions to determine if they are at equilibrium. In all cases, we are using the Haber process to synthesize ammonia, nitrogen and hydrogen producing ammonia gas, and ammonia gas colliding to produce nitrogen and hydrogen. We are given the value of K for this reaction, so we need to compare K to Q, our reaction quotient, for each set of values. In all cases, in order to solve for Q, we'll use the expression that the concentration of ammonia raised to the second divided by the concentration of nitrogen times the concentration of hydrogen cubed. So plugging in some values gives us a reaction quotient of 125,000. So in order to determine which direction the reaction shifts or which direction the reaction favors, we'll compare that value of Q to the given value of K, which again was 0.06. Obviously, 125,000 is significantly larger than 0.06, so the reaction shifts to the left, or favors reactants. Same song, second verse, same as the first. We'll plug into our reaction quotient 2 times 10 to the minus 4th squared over 1.5 times 10 to the minus 5th times 3.54 times 10 to the minus 1st cubed, to give us a reaction quotient of 6.01 times 10 to the minus 4th. So again, we will compare K to Q, the value of Q being 0.0006, the value of K given to us as 0.06. 0.06 is substantially larger than Q, than our reaction quotient. So the reaction shifts to the right, or it favors product production. Our last one, I don't have enough room at the bottom of the screen, so I'll move to the top if it's all the same to you. So for our last one, the reaction quotient would be 1 times 10 to the minus 4th squared over 5 times 1 times 10 to the minus 2nd cubed, to give us a reaction quotient of 0.002. And again, comparing K to Q, 0.002 compared to 0.06. K is greater than Q, therefore the reaction shifts to the right or favors product production. On page 14, at the very last problem, you were given equilibrium concentrations and asked to determine how it shifts. So finish page 14 by completing number 4. You can also practice this on page 16 by determining if the reaction favors the reactants or products at the concentrations given. Please pause the video, complete page 14 and 16. Now, if we are told that a reaction has reached equilibrium and we know the values it started at, we can determine the concentrations of everything else in that container or in that system by using what's known as a Rice table. A Rice table stands for the reaction, the initial concentration, the change in terms of X, the equilibrium in terms of X, and then the actual equilibrium value. So I add an extra E here because I personally like seeing my equilibrium concentrations expressed in terms of X to visualize how we got to our concentrations at equilibrium. So I kind of use a Rice E table. If any of you are chemistry majors and have seen it as just Rice, I have an extra step. So exercise 9 in our packet has us set one of these up. It says at a certain temperature, a 1 liter flask contains 0.3 moles of phosphorus trichloride and 0.008 moles of phosphorus pentachloride. After the reaction reaches equilibrium, there's 0.002 moles of chlorine gas found in the flask. Determine the value of K. So the equilibrium expression is going to be the concentrations of chlorine gas times the concentrations of chlorine trichloride, of phosphorus trichloride, over the concentration of phosphorus pentachloride. We know one of the concentrations, but in order to figure this out, we need the other two. So we can figure out what the other two values are just based off the problem that we're given if we set up a Rice table. So initially they tell us that we have this many moles of phosphorus trichloride and this many moles of phosphorus pentachloride. Since it doesn't mention the chlorine gas, it's safe to assume there was no chlorine gas in our flask when we started. As the reaction happens, phosphorus pentachloride, a reactant, is going to be used up. It's going to change at a rate of 1x, some value. It's going to decrease by 1 something. And phosphorus trichloride is going to increase by that same stoichiometric coefficient. It's going to increase by some 1 something. Chlorine gas also will increase by 1 something. So in terms of X, our reactants decrease by 1 something, and our products increase by 1 something, based off of stoichiometric coefficients. So at equilibrium, the concentration of phosphorus pentachloride would be 0.008 minus whatever that change is. And phosphorus trichloride would be 0.3 plus whatever that change is. The value of chlorine would simply be what that exchange was. Since there was none to start with, this must be the value of X, the change that we saw. So when you lay it out nice and pretty like this, our word problem actually provides us everything we need to figure out the concentrations of everyone else. So 0.298 plus 0.002 is 0.3, and 0.0087 minus 0.002 is 0.0067. And with these values in mind, we can determine our equilibrium position at this temperature. It's simply going to be the concentration of the chlorine gas times the concentration of the phosphorus trichloride over the concentration of the phosphorus pentachloride. So 0.002 times 0.3 over 0.0067. You end up with 0.0896 as our equilibrium position. So this reaction favors reactants. This reaction does not produce very many products. If you're given the equilibrium position, you can actually determine the concentrations of everyone at equilibrium, which is what exercise 8 does. Exercise 8 says nitrogen tetraoxide is used in rocket fuel to produce nitrogen dioxide. And an experiment is done where we take dinitrogen tetraoxide in a flask and allow it to reach equilibrium, with the equilibrium position being 0.1. At equilibrium, the pressure of dinitrogen tetraoxide is 2.71. So we need to figure out what is the concentration of the nitrogen dioxide. We're given Kp. So Kp would be the partial pressure of nitrogen dioxide squared over the partial pressure of dinitrogen tetraoxide to the first. Since we know what Kp equals, 0.133, we can determine this unknown value. This unknown value has to be 2 times the change based on the stoichiometric coefficient that as dinitrogen tetraoxide is used up, it would produce 2 nitrogen monoxides. So 2x squared over 2.71 has to equal 0.133. Multiplied by 2.7 on both sides, we get 2x squared equals 0.36043. Now 2x squared, distribute this square. So 2 squared is 4, x squared is x squared, and now this is just simple algebra. Divide by 4 on both sides, and we get x squared equals 0.09. Square root of 0.09, we get that the change was 0.3 atmospheres. Now that was the change. So the equilibrium pressure would be 2 times that value. So 2 times 0.3, or 0.6 atmospheres is our answer. On page 15, you'll find practice either calculating the change and determining the concentration of an unknown, or calculating K from given values. If something is not mentioned, if you're asked to find K and it doesn't say that you had some amount of products in in the system, you can assume that products start at a concentration of 0. That will be the end of Unit 7.2. I will see you next time when we talk about Le Chatelier's principle.